All right, hi everyone. It is now 1400 UTC, so it's time to start session 8 of the Amaldi meeting on it's an invited session with 3 invited talks on cosmology, society, and machine learning. And our chair for the session, it will be Francesco Fiacaro from Pisa. So Francesco, go ahead and take it away.
Thank you very much, Scott. Welcome to the session, and I think that we can start with Antonella Palmese, who will talking about probing the universe expansion with multi-messenger astronomy. Antonella, you have 40 minutes and 10 minutes for questions, and I'll give you a sign 3 minutes before the end.
Hi, everyone. Thank you so much for giving me the opportunity to speak about my work and also collaborators' work today about standard siren cosmology, mostly multi-messenger standard siren measurements. So I'll start by telling you a little bit about bright standard sirens and how also we're currently trying to use the dark energy camera to do a follow-up of gravitational wave events. Then I'll move on to telling you about binary black holes that merge in AGN disks. And then at last, I'll be telling you about dark standard sirens where we're using galaxy catalogs to measure the Hubble constant. And here's a couple of acronyms that I'm sure you're all familiar with, just to make sure that you know what I'm talking about. They're listed here in the bottom, in particular, maybe AGN you haven't seen in previous talks, active galactic nuclei, BBH is binary black holes, DCAM is the dark energy camera, and LVK obviously is the LIGO Virgo Kagra. So just to give you some context, what type of gravitational wave sources I'm talking about here, I'm talking about LIGO Virgo Kagra detection. So here's a plot that I'm sure you have seen already this week, and you'll see throughout the week several times. These are all the detections that LIGO Virgo and Kagra have made so far. So on the y-axis, you have the mass of the systems. Particularly, you have 2 objects that are in a binary and a third component, which is showing you the mass of the remnant object that is formed. In blue is the black holes, and in orange is the neutron stars. And this figure will come back later. So these are the type of sources that we're using: binary black holes, neutron star black holes, and binary neutron star mergers. Now, the topic of this talk is the Hubble constant measurements for the most part. So some motivation to try and measure the Hubble constant is the current Hubble tension. So I'm sure you're all familiar with this, but let me remind you that this is a 4 to 6 sigma discrepancy between Hubble constant measurements from the early and the late time universe. So most notably the measurements from the cosmic microwave background with Planck that are mostly close to 67 kilometers per second per megaparsec versus measurements that are coming from Cepheid anchored supernova type 1a. And so these are closer to between 70 to 74 kilometers per second per megaparsec. And here you see this nice plot from a review from Eleonora Di Valentino showing you in particular these 2 measurements given by these vertical bands and how these 2 measurements do not overlap within a few sigmas. So this is telling us that there's perhaps some systematics that we haven't properly taken into account in one of these measurements, or perhaps there is some physics beyond the flat lambda CTM model, for example, that is assumed for this specific Planck measurement. And so this is biasing somehow our results, our measurements. Getting an independent measurement of the Hubble constant can help us clarify this tension. And in particular, if we're looking for something that is coming from the late time universe, like those gravitational waves sources that we saw in the previous slide, ideally we want that to be independent of the same set of systematic that might be responsible for problems in the Cepheid anchored supernova type 1a measurement. So we want it to be independent of the distance ladder that is used in those measurements. So standard sirens do offer that possibility. In particular, we can get a luminosity distance measurement directly from the gravitational wave detection. And then if we're able to identify, for example, an electromagnetic counterpart, and that brings us to the identification of one host galaxy, we can get a redshift of that galaxy, populate this Hubble diagram and measure the distance redshift relation, which in turn lets us measure the Hubble constant. And as we go to larger redshifts, we'll see also later, we can hope to measure the entire Hubble parameter, and perhaps so get some measurements of the equation of state of dark energy, for example, or omega matter. So what types of standard sirens currently exist? So here is I try to put them together into 3 different classes. So the first one is the most obvious one is the bright standard sirens. Hopefully that's where we are with most binary neutral star mergers, for which hopefully we'll be able to identify electromagnetic counterparts. Maybe in some cases for some neutral star black holes, we'll be able to do that. But in any case, in this case, we have a unique host galaxy. And so that's where the redshift in that Hubble diagram is coming from. The second case, we might have no counterpart detected, as is expected, potentially for most binary black hole mergers and neutral star black holes. And in this case, what we can do is take into account all of the potential host galaxies that fall within the localization volume from the gravitational wave detection. So here is a 2D localization area in the sky, 50 and 90% credible interval for this specific gravitational wave detection from 2017. And so what we do is basically take into account this distribution of galaxies over the entire this area, and particular take into account the redshift distribution of those galaxies along the line of sight within those area. There's also another way of doing standard siren measurements that I'm not going to discuss here, but I'll just mention that it's also possible to get standard siren measurements that do not need multi-messenger observations and just use gravitational waves. And in this case, the redshift is going to be coming from the reshifted masses that can be measured from the gravitational waves. And so one can make some assumptions perhaps about the mass distribution to get that redshift information. But this is one that I will not be discussing today. So let me start with bright standard sirens. So the objects of interest in this case are for the most part binary neutral star mergers. So and this is because we expect a range of different wavelength detections potentially for this type of mergers. So we do expect, if we are on axis at least, to see a gamma ray burst coming from the relativistic jet. You see in this animation that's coming from this magenta jet. We also expect to see some ejecta from a kilonova. Here in the animation, it was in purple and white. That is detectable between the UV to optical to near infrared wavelengths. And we also expect to see an afterglow potentially coming from interaction of the jet or even the kilonova ejecta with the surrounding material. And that is potentially something we can see at different wavelengths, all the way from the X-rays to the optical to the radio wavelengths. So just a few words about the kilonova in particular, because that's something that is really relevant to also the dark energy camera follow-up that we do, since that's optical, that's operating at optical wavelengths. So this is a thermal transit that we expect to see to be powered from these heavy arc process elements that are formed in this kilonova ejecta. And so here you see a nice figure from the detection that was made also with DCAM of the kilonova associated with GW170817. And it's in particular the detection of this kilonova that initially let us pinpoint the exact location of the merger so that we could associate it with a specific host galaxy. And so that was what enabled the first bright standard siren measurement. This was led by the LIGO and Virgo collaboration. Here you see the posterior on the Hubble constant in blue, as it compares with the 1 and 2 sigma constraints from, at least at the time, the Planck and the Shu measurements given by these vertical bands in green and orange. The 1 and 2 sigma constraints from the standard siren measurement are given by these vertical dashed and dot lines. So obviously they're much broader because this is only one event. But eventually, as we'll see, this is a very interesting way of measuring the Hubble constant. We'll get to the precision that is needed. And it's also useful to use this specific type of measurement because, one, it's self-calibrating. We said earlier, we don't need a distance ladder to do this. So we'll be sensitive to a completely different set of systematics compared to what happens with standard candles. And it's also, in this case, cosmological model independent in that we don't have to assume a background cosmology because we're mostly looking at objects within 200 megaparsecs, or in this case, it was 40 megaparsecs. Some limitations that one could mention are, first of all, the peculiar velocity of the host galaxy. Exactly because these objects are so nearby, it's also very important to take into account that galaxies are not only, the galaxy's redshift contribution is not only coming from the cosmological expansion of the universe, but also from some peculiar motion of the galaxies. The other thing to take into account is that there is a degeneracy between the inclination angle of the binary and the luminosity distance. And so this translates into a degeneracy between the inclination angle here on the y-axis and the Hubble constant. In other words, a lot of that uncertainty that we find in the specific standard size measurement is actually coming from this degeneracy. And there's a way that we can hope to break this degeneracy by making some constraints on the viewing angle from electromagnetic observations of the counterpart. And this can bring some improvement of a factor of a few. So this was done by several works in the past, and we have redone it using very recently using the latest observations of the afterglow of GW 170817. So using data beyond 3 years, we use this hydrodynamic simulation-based code called JetFit to model the afterglow all the way from the X-ray to the radio, and you see the light curves from the X-ray to the radio here in these plots from bottom to top, and our best fit given by the lines. And so this way, we're able to measure the viewing angle from the afterglow. So here you see the degeneracy from the gravitational wave data in the luminosity distance versus viewing angle in blue, our constraints from the afterglow in orange, and our combined posterior shown here in gray. And that gives us a viewing angle of about 30 degrees. So given that, we can actually, well, this was actually a joint gravitational wave and electromagnetic data inference that also included the host galaxy peculiar velocity treatment following Nicolau et al. 2019. And so here is the result, the posterior that we get on H0. Our fiducial constraint is shown by the black solid line with our constraint shown here. We also tested the effect of different assumptions that were made in the jet modeling. In particular, we varied a couple of different priors for different parameters to see what effect that would have on the Hubble constant, in particular on the viewing angle estimate. And one of the priors that had the largest effect on the viewing angle was basically what is related to the jet opening angle. So we looked into what that effect would have on the Hubble constant estimate. And here you see different prior assumptions shown by these gray contours, gray lines, and we don't see a huge shift between these different parameters. So we're pretty confident that at least within the set of hydrodynamic simulations, our result is quite robust. We find a precision of about 7%, which compared to the 14% precision that was from 2017, the paper that I also showed earlier, led by the LVC, is quite substantial. Here you see the original constraint in dark orange, but we should really compare this to the constraints from Nicolau et al. Because the assumptions that we made, the framework that we used to take into account the peculiar velocity actually would make the uncertainty coming from the peculiar velocity a little bit broader. So that's giving us this light orange curve. So it's a little bit even better improvement if you compare it to that posterior. Okay, so now let me move on to telling you about the future. And this is so far the only confident association that we have with a gravitational wave event. But what we're doing right now is trying to get the next gravitational wave electromagnetic counterpart using the dark energy camera. So I'm sure all of you are aware that the fourth LIGO observing run has started. And so we're using now the dark energy camera, or DCAM, which is a 3 square degree field of view camera mounted on the 4-meter telescope in Chile, the Blanco telescope at Cerro Tololo Inter-American Observatory, to perform this follow-up. So this is a part of a survey, an SF NORLAB survey that will run until 2025 with full overlap with the fourth observing run. We want to follow up all kinds of sources, binary neutron stars, neutron star black hole mergers, and also massive and well-localized binary black holes, potentially one strongly lensed candidate. Expectations are it's possible we'll find the first one during '04, but who knows? For a total of equivalent to about 24 full nights of target of opportunity. So this is going to be disruptive target of opportunity observations. So this is something that I'm carrying out with Igor Andreoni and obviously a full team of great collaborators. So here you see a little animation showing you how we could cover observations with the dark energy camera of the simulated event that we have from a set of simulations that look like '04 gravitational wave event. After we get the observations that we have planned this way, we have a rapid GPU-enabled difference imaging pipeline that we run to find new transients. And we are planning to publicly report on the transient name server and also through the GCNs, the gamma ray coordinate network, our findings. So stay tuned for some results from us. So where will this bring us in terms of standard science? So the expectations that we had for a couple of years already is that to reach that 2% precision on H0, that we need to understand whether we lie more on the CMB side or on the local universe side, is about 50 events. So, here I'm showing you the precision on H0 as a function of the number of events that are combined, and this is the orange line shows you how many events we need to reach a specific precision. Now, one can hope to bring that down to this blue curve is if one is able to make some measurements of the viewing angle from the electromagnetic observation. So here I'm showing this, I'm labeling this as a kilonova viewing angle, just because I'm assuming something that looks like some of the kilonova viewing angle estimates that were made for GW170817. So with a broader, a slightly broader constraint than what I showed you for the afterglow observed for 3.5 years. So this is about a 10-degree 1 sigma uncertainty. And so we can, with that type of measurement, we can beat this orange line down to the blue line and potentially get to that 2% uncertainty with a dozen event or so. So this is something that it possibly, perhaps in a very optimistic scenario, we could hope to reach during '04. So here the shaded regions show you what one could hope to achieve if all of the ZTF and DCOM, so Zwicky Transient Facility follow-up, and also the DCOM triggers that we have, we'll be able to find most of the counterparts that we can, that we're allowed to follow up to trigger on. So take this as the most optimistic scenario, but hopefully we'll be somewhere between, a few and 10. Now, going back to this picture and moving on to the binary black holes, I just want to highlight the fact that a few of these component masses seem to fall within this square here, which I labeled mass gap. So this is the allocation in the mass distribution, what we don't expect to see black hole, at least formed through standard stellar evolution because of pair instability and pulsational pair instability supernova. So the exact position of this mass gap is highly debated, whether that's between 50 or 70 or 80 and 120 solar masses or so. It's debated, but it seems pretty confident that we have some very probable objects in this region. So this is one reason as to why we might be interested in looking for formation channels that go beyond standard stellar evolution for these detections. And also, it seems from population analysis of gravitational waves that there isn't just one channel that is producing all of the binary black holes that are detected. So there's potentially a mixture of those. And so that's why here I'm telling you about the specific one, which is binary black holes that form and merge in AGN disks. So the reason why this is a great environment to produce these black hole mergers in the mass gap is that you can hope to form and retain black holes that are more massive than what you would expect in the field. As for example, if you believe that there are migration traps where different black holes might be able to find each other and form binaries and merge, and also they will not be usually kicked away from very far from the AGN because of very strong gravitational field, as opposed to what would happen, for example, if you have a merger in a globular cluster. It's highly likely that it would be kicked out, and so it's harder to produce second generation or third generation black holes that can merge with other black holes. But what's very interesting for me as an observer is that if we have black holes merging in AGN disk where there's gas present, they could give rise to an electromagnetic counterpart. And so this has been theorized in several works, and also has some potentially interesting observational data. So there have been so far about 7 flares that have been found in coincidence with different gravitational events, most notably GW190521. And here you see the light curve from the 3K transient facility in G and R bands. So this is the magnitude as a function of time. And here you see how there was a flare in these 2 bands after the detection of the gravitational wave event, which is given by this vertical line. So this was very compelling. However, what we found for this specific event is that using structure functions and IGN luminosity functions, well, we found that it was very likely that there was, a flare of this kind, this magnitude at the same location at the same time of GW190521, simply because this event had a very, very large localization volume. Also because this was one of the furthest events that was detected in the previous observing run. So lots of volume includes lots of AGNs, and AGNs tend to vary all the time. So this was a 70% probability of chance coincident that we found. In some sense, this might have been a little pessimistic, but in any case, it's hard to make a confident association between that flare and the gravitational wave event. But the interesting question that we wanted to address is whether eventually it will be possible to make a confident association between binary black hole and AGN flares. So we wanted to do this at a population level. So we're not trying to say this specific flare is associated with this specific binary black hole merger, but we're trying to say, given the population of AGN flares that we have so far observed, can we say that there is a connection between the two? So we built this Bayesian formalism that is basically looking for signal AGN, so those that are actually producing a flare that is associated with the binary black hole merger, over some background AGNs that might be varying at the same time as the gravitational wave event. But the idea is that these two populations will have different distributions, at least in 3D space. And so eventually we'll be able to discern between the two and basically constrain this parameter lambda, which is the fraction of binary black holes that give rise to AGN flares. So our output will be, the first output at least of this work, is a posterior on lambda, given the gravitational wave and the electromagnetic waves data. So here is just some examples of the simulations that we made in this paper for a true value of lambda of 20% after some number of follow-up observations. We then went ahead and asked, what does this mean for the upcoming observing run that at the time was upcoming 04, because this is something we worked on 2 years ago. And so we created realistic simulations of 04 binary black hole mergers, at least what seemed to be realistic at the time. So take this with a grain of salt, because back then, at least, we thought, Virgo would be operating and Kagra would be operating. So this is a little bit optimistic. But what we found is that a confident association between the two would be possible at the end of 04 if lambda, the true value of lambda, is at least 10%. So at least 10% of these objects are, giving rise to these AGN flares, which seem to be indicated by the fact that what the ZTF follow-up is finding. Then we should be able to say that with confidence in this observing run. So here is the number of events needed to reach a confident association on the y-axis, a function of the true value of the fraction of binary black holes inducing an AGN flare. So different lines, take them just as different types of localization volumes, from larger to better localized. So obviously you'll need a smaller number of follow-up observations if you have a better localization, because your background flares go down. And again, this in all cases, this number will be lower if a larger fraction of binary black holes is actually inducing an AGN flare. So for the case here that we suggest to follow up is like the best, better localized and more massive events in order to minimize the background flares. The line that we're looking at is this orange one. So potentially we might only need something like a dozen of these observations, again, in this quite optimistic scenario. But the point I want to make here is that it could be useful to take into account this formalism for cosmology. So first, if you are believing that there is an association, for example, between that AGN flare and GW 521, then you can go ahead and make a simple bright standard siren measurement. And this is something that several people have done in the literature. Also taking into account, for example, the possibility that this might have been an eccentric merger. What we are trying to suggest here is that, if we are not sure about the association, we can still use this data to make a standard siren measurement, as long as we're taking that we are not sure into account in our formalism. So in some sense, this is a hybrid bright and dark standard siren method, in that we are looking at potential counterparts, but there might be multiple counterparts at once. And so in that, it's more similar to the dark standard siren method, in which we take into account all the potential host galaxies in the localization volume, but it's a much smaller number of objects that we're taking into account in this case. So here we're saying, using the same formalism you saw before, but we're adding in the cosmology. And so basically allowing to open our parameter space to beyond lambda, and here, for example, including the Hubble constant. So going forward, because now we're talking about binary black holes well beyond something like 200 megaparsecs, that we might wish in the next year or so for binary intrastar mergers. Then in this case, we can also take into account all other cosmological parameters. So for example, we can start trying to measure omega matter or dark energy equation of state W. For the most part, however, we're really sensitive to the Hubble constant, which is why you'll see in these plots mostly the Hubble constant. And this is because the better localized events are those that are really driving the constraints, and the better localized events. And again, by better localized, I mean better volume. This will be the most nearby ones. And so this is why H0 is what we're most sensitive to. So here we make some simulations, assuming that something like between 20 and 80% of the binary black holes may be coming from the AGN channel. So this is something that other people have estimated. And we rescale this to take into account unobscured AGNs, where we can hope to see the flare more easily, at least in the optical. And so what we find is this constraints that you see here in the bottom right. So this is the precision on H0 as a function of combined number of events. And we find that with about 2 years of LIGO, Virgo, and Kagra running at design sensitivity, we can reach a precision that is between 3 and 8%. And that specific number will depend on a few different things. Specifically here, you see the different colors are showing you different values of the true value of lambda. So if we're only 5% of the binary black holes are producing an AGN flare, then we might get this purple line, and all the way to 30%, might get a better constraint. This is shown by this red points. There's other things that one might want to take into account: the probability of flaring of each AGN, and also different types of priors on omega matter. But overall, this is the precision that we're looking at. And again, in some way, this is still a little bit optimistic, like the forecast that I showed you earlier, in that we're assuming that Virgo and Kagra are working. So a little optimistic if you're comparing this with the current 04 observing run. With the A+ sensitivity, so the next upgrade, we might be able to reach within something that is close to a year, a 2 to 6% precision in H0. And again, this is shown here in the last points. Now, one can also apply the same method to not take into account all the flares, but simply take into account the AGN catalogs. So in some way, this is a little bit easier because you don't need to do expensive follow-up observations, although I see the type of observations done really well by this Wiki Transient Facility and in the future by LSST, the Rubin LSST. But if one doesn't want to do that, for example, one can take into account AGN catalogs. But now, while before you could have just looked at nuclear transients, now you need to have to take into account also the AGN catalog completeness. And the expectations here that we find is about 5 to 10% precision on the Hubble constant with about 1 year of LIGO Virgo and Kagra run at the sign sensitivity. So in some way, this, if the AGN channel is really contributing a significant fraction of the binary black hole detections, then this could be potentially more constraining than what we find from the dark standard sirens, because the dark standard sirens have to marginalize, as we'll see in a little bit, over a larger number of galaxies than just those that host an active galactic nucleus. So now the last part is on dark standard sirens. So here I'm showing you a slide on simulations just to give you a proof of principle of how dark standard siren measurements work. So these are some simplistic simulations of gravitational wave events on top of a dark energy survey like galaxy simulation. And here you can see the recovered single event posteriors on the Hubble constant on this top panel given by this gray lines. A few of those are highlighted in colors so that you can see better what each of those look like. And you'll see that there are multiple peaks in the H0 distribution corresponding to different values of H0. And this is totally expected in the dark standard siren method because in the case of a bright standard siren, you only have one galaxy. Even with dark siren, you might just have one over density along that line of sight. And so that specific redshift will correspond to a given value of H0 will correspond to one value of H0 given a distance value from the gravitational wave event. But now if you have multiple redshift values corresponding to multiple galaxies or multiple over densities along that line of sight, then you will get multiple values of the Hubble constant for that one event. The important thing is that, at least here, right, we're simulating events in galaxies. We hope binary black holes are happening in galaxies. So we will always have the galaxy, that is at the right redshift that is giving support to this posterior distribution at the input value of H0, which in this case was 70 kilometers per second per megaparsec, given by this vertical line. Now, the important thing is that after we combine enough events, we're able to recover the input value of the Hubble constant. So the combined posterior from all the events is shown here by this solid black line. And this is still the case, even if we increase our uncertainty, for example, on the luminosity distance or on the redshift. So what this does is simply to make this posterior, especially the single event posteriors, a little bit broader. And so the important point here to bring home is that we cannot do precision cosmology with just one or a few dark standard sirens. The numbers we're looking at are really in the hundreds. And we'll get there eventually with binary black holes. So where do we stand currently in terms of observations? I already mentioned this earlier, but during the last observing run, 03, the third one, there were a bunch of different alerts, more than 50 alerts, but other than that, there was no high confidence counterpart that was associated with any of those gravitational wave alerts. And so all we were left with, at least coming from the last observing run, after 170817 was discovered in the previous one, was only to make a dark standard siren measurement, apart from that candidate counterpart from GW19 0521. So this was done by the LIGO Virgo and Chiron collaborations using the GLADE Plus Galaxy Catalog and using about 47 sources. I'm probably not the best one to give justice to this result since I'm not in LIGO Virgo and Chiron, but I thought it's important to show where we stand in terms of this result. So here is the fiducial constraint given by this orange line here, and after combining with GW170817, you get this blue posterior, and the result is shown here. So this gives about a 40% improvement compared to the previous observing run. But one of the things that were found in this study is a strong dependence on the assumptions about the black hole populations. And so this is shown by this pink to the blue lines here on the right, just for varying assumptions about the this mass distribution of the black holes. So what we did is to only focus on some well-localized events, the best localized events that we got from the previous observing run, and only consider those that had high galaxy catalog completeness in that high probability region. In particular, we used the DESI legacy survey imaging catalog. So here we're using photometric redshifts for the most part. So by doing this, we are focusing on events that do have a lot of support in the redshift distribution. And so we are less sensitive to the population assumptions that are made, that are bringing a lot of the constraining power in the Hubble constant posterior when the galaxy catalog do not provide a lot of constraining power, maybe because they're too shallow in that specific region of the sky. And so here is the events that we took into account in color, and the orange regions is where we have galaxy catalogs from the legacy survey specifically. Our final constraint on the dark standard siren from the dark standard siren is shown here in blue. And once we combine that with GW170817, we get a posterior a constraint that is reported here. So this is about a 30% improvement to the bright standard siren measurement coming from the dark siren. So it starts to become an interesting addition to the bright standard siren case, given that the bright standard sirens seem to be so rare. Perhaps I'll say a few words about dark standard siren systematics that we have taken into account, specifically the photometric redshifts, because I mentioned earlier that we're using photometric redshift catalogs. So we have measured on a validation sample with spectroscopic redshift the bias that we expect and corrected for it in our posterior on H0. Other things that are very important to take into account is gravitational wave selection effects. In the future, I think expectation on the specific dark siren constraints that are coming from different binary black hole formation scenarios will be very important to explore, and I know many people have started doing so. Now, the last thing I want to mention is something that I get asked a lot when I talk about dark standard sirens. So there was recently a paper, well, now almost 2 years ago, time flies, a paper that was claiming that the posterior on the Hubble constant from dark standard sirens is in general biased relative to the true value, even when making optimistic assumptions. And they found that the bias depends on the realization of the underlying galaxy sample and the precision of the gravitational wave source distance measurement. So in particular, on this point of the precision of the gravitational wave distance measurement is what this plot is showing. So for uncertainties that go from 10 to 30% of the true value of the luminosity distance, for example, for the specific line of sight, they find that the posterior shifts from the solid to the dashed to the dotted lines here. So this is quite worrisome, I get, for a lot of people. So we came together with a lot of us working on dark standard sirens and tried to understand what was going on. So we recently published this paper where we show that, first of all, it's not the method itself that doesn't work, but it's mismodeling and misinterpretation, and specifically of observed versus true variables, and implementation of the Bayesian framework, which are not consistent with the way the mock data was generated, that led to some of those biases. And so we tried to come up with some possible inconsistencies that people might be falling for. So specifically here we are listing 4, and specifically this one is the one that we tried to recreate for this specific plot that was found in this other paper, where we varied the uncertainty on the luminosity distance from 10 to 30% of the true value of the luminosity distance. But if you're doing that, you're putting into your data set some dependence of the true value of the luminosity distance. And so this has to be taken into account when you write the posterior on the Hubble constant, otherwise you might lead to biases. However, when we do everything correctly and consistently between the way we generate the data and the way we calculate our H0 posterior, we find that our posterior is unbiased. So this is just an example for different lines of sight, for different localization areas. And here is a PP plot. Without going into detail, you want this to be a one-to-one relation if you're doing a population analysis of different injections for H0 values between across the entire prior range that we take into account here. I think it's between 40 and 120 kilometers per second per megaparsec. So it's an interesting study if you're interested also in learning more about the method and how not to incur in biases. Obviously, things are much more complicated as we get to the 2 to 5% statistical precision, which might be possible after a few hundred detections with LIGO, Virgo, and Kagra at the sign sensitivity. Then we need to really be worrying about all the systematics that might be coming at play. So I think I'm out of time, so I'll leave you with this conclusion slide. Hopefully I convinced you that there is a lot of interesting things that we can do by combining multi-messenger observations from gravitational wave observations and also, for the most part, optical sky surveys. And I'll stop here. You have my contact here if you'd like to ask questions and you don't have time today.
Thank you very much, Antonella, for the very nice talk. We are clapping our hands, of course, and there is room for questions in the question and answer window.
We should also mention, in case anyone wants to actually ask a question vocally, we can unmute you. So just reuse your raise your hand feature on Zoom, and we'll grab you.
Let me break the ice. Did you have a look to the perspective with the third generation? What is waiting us?
That's a very good point. Well, I haven't myself. I should. I'm very interested in particular in this, afterglow measurements that could be possible. But yeah, definitely people have looked. I think for the most part, in terms of standard SRN cosmology, the question that always comes is, is it going to be interesting to measure to better precision like H0 in 10, 15 years? And probably, for the most part, we will not be competitive with other type of measurements for, especially for dark energy equation of state. And so, obviously there will be much better, we get 2 very high signal to noise detections of binary neutral stars. We find the counterpart that gives us a sub% precision on H0. So that's kind of the expectation. And it's remarkable. But the question is always, how will that be interesting in 10, 15 years? And I don't know, maybe more like 15 years. And I don't know.
Thank you.
We'll also get some very well localized dark standard sirens that will only have a few galaxies in them, maybe even one. So Satya from Penn State with his students there, they have done some very nice work showing how this will be very powerful in next generation detectors.
Thank you. Some other question around.
And people can contact me. I'm sure that a lot of people are just watching things at different times, right? So people can contact me here if they wish to ask questions offline.
I have a second one since I'm somewhat far away from this and more with the detector side. When you go to large Z, then you won't have any optical counterpart because you're too faint or you're not able to localize things. Will the dark siren work better at very high Z, you think? It's promising.
Yeah, I think and high redshift, perhaps the answer is with the spectral siren method, the one that I have not talked about in this talk. So yeah, right. So that's where I think there's also some complementarity between these different methods, right? We can get maybe some very nice and precise measurements of H0 from counterpart detections, but we cannot go to high redshift versus the spectral siren really gains from the larger numbers, the larger statistics, where you have more volume, so closer to the detection horizon, and so that will give you very interesting constraints in that redshift range. So I remember at least for current generation detectors, I remember Will Farr's paper, a few % precision on the Hubble parameter around redshift 0.8, and that will be completely different with next generation detectors going at larger redshifts. So yes, for sure, spectral sirens I think is the way at larger redshifts.
So it seems that the talk was very clear, and people then will profit from the contacts. I think we can thank Antonella again. Clapping your hands, of course.
Thank you.
And for all the attendants, the attendees, we will meet again at the hour, whatever your time zone is. So we have 10 minutes, something like 12-minute relax, and then we'll go on with the next talk. Thank you very much, and see you soon. We are at the hour, so we can continue our plenary session with Kathryne Daniel, the Steward Observatory, who will talk us about collaboration on global and local scales, the power of the two-eyed seeing approach in gravitational wave science. Thank you, Kathryne. I will warn you 3 minutes before the end. Thank you.
Thank you so much. There we are. So thank you so much. I'm really happy to be here. I want to take just a moment to introduce myself. I'm a person who wears multiple hats. I'll talk for just a moment about my science in a few minutes. But I also wear the hat as Deputy Director for Cosmic Explorer and the co-founder and co-director of the Society of Indigenous Physicists. My science specifically is in galactic dynamics, but I've taken an interest, deep interest in policy in the past few years. But before I begin, I want to extend my gratitude to all my relations and to recognize that the many generations that came before me, that it was through their sacrifice and difficult choices and love before I was even conceived that gave me the opportunity ultimately to be here talking to you today. I also want to extend my gratitude to my colleagues and the gravitational wave community for organizing this and for the following events. So far, I've had a wonderful time. This is my first Amaldi conference, and it's been a great experience so far. Also to the NSF, NASA, and the Heising-Simons Foundation who've supported my work and made much of what I'll be talking to you about today possible. But finally, I want to acknowledge that I'm currently standing on the ancestral lands of the Munsee Lenape. So I'm in New York City on Manhattan Island. And actually, if I just look out my window right here, I'm looking over Broadway, which is the old Lenape trade route running up and down the island. And Manhattan was sold to the Dutch in the mid 1600s for about $25, or the equivalent of $25 today in US dollars, which was really just marked the beginning of a long history of forced exile, where Wall Street, if you know Manhattan, is named after the wall that they built to keep the Lenape and the English actually out. So I want to acknowledge the people, the Lenape, who were the stewards of this land for millennia and who maintained a deep connection to our relatives here, their relatives here, animal, insect, water, sky, earth, throughout the generations. And my hope that more Lenape voices will be heard in New York City and on this island, again, moving forward. So when I was small, my grandfather would play a game with me. And it would go something like this. He would say, look at that hawk. And he would say, what do you think it's like to be that hawk? And he would tell me to watch it, its movements. He would say, what is it doing? What do you think it's thinking? And then he would take it to another step and he would say, now I want you to imagine that you're on the back of the hawk, that you're sitting there. What does the wind feel like? What does it look like to be up there looking down at us? And then he would finally take it a final step and he would say, to be the bird. Think like the bird, know like the bird. And what he was doing really was giving me lessons in perspective. And these were lessons to get me out of my own reality about the world, my ideas about the world. And he was teaching me that rather than living in my own head, to be in the world and with the world and in relationship with everything around me. And most importantly, he was teaching me to see with eyes born not of my own experience, that there is in fact no central perspective, much less that it's mine. So this is very similar to the notion of two-eyed seeing, which I will explain in a moment. I want to emphasize that it is not the same thing as empathy, though it's related. And as far as I know, there isn't a word for this notion in the English language. And that notion is to gain a deep understanding by accepting that multiple perspectives can be truth. So there are many audiences listening to this talk. And what I mean by that is there are people with multiple identities and in multiple places in their lives. So there are people who are students, there are faculty emeritus, there are Indigenous people and not, there are folks from the gravitational wave community and elsewhere, colleagues, friends, and places where those spheres overlap. And the reason that I'm bringing that up in this context is that I want to recognize that each person has their own perspective. And importantly, that each person will hear the same words through their own lens. So I hope to weave a story here that, that has a message for each person. But I also challenge you to listen for the other messages as well. So two-eyed seeing is, as far as I can tell, something that was coined by Albert Marshall, who's an elder. And this is the idea that there is a depth of perspective or a strengthening of knowledge when a person is able to simultaneously see through both an indigenous worldview and a Western scientific lens. And I'm going to expand upon this notion to talk about how we as a community set our science priorities, and importantly, how that is also connected to the way in which we do science. So I think oftentimes we think about these as two separate two separate things, but I'd like to argue that there really isn't a division between them. And then I'm going to also build on a concrete example, which is Cosmic Explorer, and how we're using this perspective and approach in the way that we do gravitational wave science. But first, I just want to give a quick note on what it is that I do and how I came to be here today. So my science is galactic dynamics. And what I look at effectively and where my interests lie is how galaxies evolve themselves through their own internal dynamics. And so when we look at galaxies at high redshift, we see these sort of amorphous, interesting, small objects. But in the local universe, galaxies have ubiquitous features, particularly spiral galaxies, of being very flat and having spiral arms, and many of them have bars in their center, bulges with interesting shapes and warps. And the questions that I like to ask are, how do those structures work, and how do they evolve galaxies from the inside? So that's just an introduction to who I am and what my science is. And through this, I became, I was involved in the Astro 2020 decadal review through the National Academies. So I want to describe what this is and how this connects to what I'll be talking about today. So Astro 2020 is the name given to the most recent decadal review from the National Academies of Sciences, Engineering, and Mathematics, or sorry, excuse me, Medicine. So, so effectively, what this is it's an overview of the current state of the field. So that is astronomy and astrophysics. There are many fields that do this, and astronomy and astrophysics has been doing this for 70 years now. So, so this is a huge endeavor. It's a rigorous community process by which we identify the priorities for the next decade in science and technology research to support that science, and then develop a comprehensive strategy to advance those frontiers. So in order to do this, it begins with a call from the community for white papers. And those white papers are in the hundreds and distributed amongst several panels. The panels, there are science panels, there are program panels, and this last decadal was a panel on the state of the profession and societal impacts. And that was the panel on which I served. So the process is that each of these panels reads the white papers and develops a 50 to 100 page report. And that report gives evidence-based recommendations to a steering committee. And then the steering committee compiles those reports and elevates only the most important and pressing and exciting recommendations to the summary report. So if you've read the Astro 2020 Decadal, you've likely read the summary report, which has multiple chapters. So in the Astro 2020 Decadal, gravitational wave astrophysics was identified as one of the most exciting frontiers in science that is central to many crucial science questions. So there's probably no argument with that here, but it is incredibly exciting that this was elevated as one of the most important recommendations for the decade in astronomy and astrophysics, which of course is connected closely to the physics world as well. Cosmic Explorer, which is the next generation ground-based gravitational wave instrument in the United States, was specifically named 24 times in the Astro 2020 Decadal. So in this process, and particularly in this review, the question was addressed, how do we do the science? And so I'm going to play off the notion of two-eyed seeing here, where we can think of the image on the left as our left eye and the image on the right as what we might see with a right eye. In 2020, the question that was perhaps one of the most burning questions in the minds of astronomy and astrophysics was the construction of the 30-meter telescope on Mauna Kea. So on the left-hand side, this is what an astronomer might see, thinking about the summit of Mauna Kea, and that is that there, it houses some of the most incredible observatories in the world with some of the best seeing in the world. And on the right-hand side is how a Kanaka Maoli, meaning a person who's indigenous to Hawaii, might perceive Mauna Kea, and that is as an embodied, storied landscape that is deeply connected to their identity and is fundamental to their physical and well-being and spiritual understanding of the world. So in 2020, and actually 2019 through 2021, because the 2020 Astro 2020 was actually published in 2021, because 2020 was a difficult year for everybody. Then these two notions seem to be incommensurate. So what I'm showing in the center here is 2019, where Kanaka Maoli blocked the access road for construction of the TMT on Mauna Kea. And this became something that was a central conversation amongst astronomers and astrophysicists who were deeply invested in TMT and in understanding how we can try to move through this moment. So this is the panel that I served on, and I'm showing you these faces to really highlight the fact that this report was something that was written by a number of folks, and truly this was something like 15-eyed seeing. I mean, it was an incredible experience. I learned so much from working with these folks. But what we realized is that we needed to open up the way, we needed to change the process enough that we were able to hear and receive white papers or something similar to white papers from the community beyond the astronomy and astrophysics community. And so when we used this novel approach of opening up the feedback that we received to include members of the community outside of the astronomy and astrophysics community, we received many papers that helped to guide the way that we wrote this report. And this particular paper was something that was central in the way that we reconceptualized how we can approach this situation where there seemed to be an impasse. And that was through relationship and building connections between the astronomy community and the local and indigenous communities. So that is to say that a third way opened up, and that third way is through relationship. And the recommendation that we made was elevated to the top report. So this is another one of the few most important recommendations from the Astro 2020 decadal. And that is that the astronomy community, with experts from other experienced disciplines, that we work with local communities in order to develop a community-based model for astronomy. So one of the reasons this is incredibly important, and I guess I'll back up for just a second, is that Astro 2020 is used by Congress to identify the amount of funding that is necessary for the field and how that funding will be distributed. So this is a message to the NSF, to NASA, to the DOE, and has played a central role in the development of the funding structures that we use in order to fund the projects that we do. So particularly in this case, facility management and facility design. So what is a community-based model? This is not new. This is something that, so community-based models are used in healthcare and forestry and archaeology and several disciplines, but it hasn't been adopted yet by astronomy and physics. So the process goes something like this. We ask the question of who are the people who are impacted by, in this case, a facility. And then we enter into ongoing dialogue and consultation, where consultation has a specific meaning. Consultation is really about communicating fully about the project, and there being an iterative process of understanding and aligning of values and goals. So this allows for the development of a power sharing model, and that power sharing model respects the timeline of all parties, and community members are a part of the decision-making process. And this really, it ensures mutual benefit for all parties involved. So this is something that is beginning to be developed now on Mauna Kea, and hopefully will be part of the process for any facilities moving forward. And there are many supports that that a person could lean on to help develop these models, all the way from international to local institutional supports. And so I want to talk for a moment about what those might be. So in the international sphere, I'm going to talk about two particular declarations that have been incredible resources. So one of those is the UN Declaration on the Rights of Indigenous Peoples, or UNDRIP. And what this is it's something that defines the rights and codifies the rights of Indigenous peoples to participate in the decisions that impact the lands, territories, and other resources that are important to those communities. So this is a long read, but it is truly fantastic if you are a person who is interested in the way that we do science, and in particular, how the facilities that we use to do observations, and also the institutions that house us, how we can be in better relation with Indigenous communities. So the next is FPIC. So this is something that is housed actually inside of UNDRIP, but FPIC stands for Free, Prior, and Informed Consent. So just to clarify what each of those means, free is without coercion, intimidation, or manipulation. Prior is consent that is sought in advance of any activities, where there's respect given to the timeline of Indigenous decision-making processes. Informed means that there's information on all of the aspects of the project, that those are provided to the community, and then the recognition that consent can be revoked at any time. So this means that, particularly that last point, what this implies is that it's extremely important that we be in close communication and dialogue or consultation, to use the formal word, with Indigenous communities around the project, any project as it develops. So I used a graphic here that I thought was really nice. This is actually from the Nature Conservancy, describing FPIC and what it really embodies. So that is that there are three pillars upon which it stands. One is that it adheres to a standard. In other words, that that your project aligns with international law. The next is the process of iterative collaboration with Indigenous people and local communities. And finally, that to be in relationship or engage in equitable partnership and trust building with those communities. And by having those three components, that this really is the nature and what is written into the Human Rights Declaration on Free, Prior, and Informed Consent. So these are international declarations. On the federal level, and I can only speak to US federal law. If you're from other countries, then you'll have to, I'm sure that there are policies that are maybe similar or distinct from these, but if you are in the US, NEPA and NHPA are two acts that are for environmental protection and historical protection that are invoked anytime a project that is using federal funding breaks ground, so to speak. So this is just to protect, to investigate the environment, to ensure that the environmental impacts are minimized, and to ensure that archaeological sites, for example, and historical sites are not disturbed. So, so these are two acts that if you have been involved in facility design in the US, you're probably familiar with. The landscape, though, is changing rapidly. And in particular, there are multiple memoranda that have been coming out from the Biden administration, where one of those is the Memorandum on Tribal Consultation and Strengthening Nation-to-Nation Relationships. So in this case, what that means is the nation-to-nation is the United States and Native nations. So if you are using federal funding, then it's important to adhere to this particular memorandum and to ensure that there is regular, meaningful, and robust consultation between your project, the funding agency, and Native nations that are impacted by that project. And then the American Declaration on the Rights of Indigenous Peoples, which entitles Indigenous peoples to the use and protection of their ancestral lands. So that is an incredibly important declaration to keep in mind, because every location in the United States is the ancestral land of Indigenous peoples. And then there are institutional policies. So institutional policies are consultation policies and guidelines. I'm giving an example of the University of Arizona's. That's because that's where I'm from. Again, this is an evolving landscape. Your institution may have one of these policies or guidelines, and it's also something that may be in development if you're in the United States. So this can be an incredibly useful guide, and there are resources at your institution to help you navigate not just the legal landscape, but also to be able to engage meaningfully and ethically with Indigenous communities. Okay, so I promised that I would give an example, a concrete example using Cosmic Explorer. So Cosmic Explorer, just to remind you, is the next generation ground-based gravitational wave observatory. We're in a really exciting moment right now because we've recently learned that a series of significant proposals are recommended for funding by the NSF. So we're really excited. We're really excited to get going on some of that work. I encourage you to check out our website to join the consortium. It's a growing project where we've got a lot of momentum, and there's a lot to be done. So the concept of Cosmic Explorer is based on the LIGO concept, which is to say that they are two L-shaped facilities, but the arm lengths or the beam lengths for each of those, one of them will be 20 kilometers to a side and the other will be 40 kilometers to a side. And what this does is it unlocks an unprecedented reach and science capabilities for Cosmic Explorer. A few talks, there have been Jocelyn Reed and Brand Slagmelin have given some talks already talking about the science capabilities for Cosmic Explorer, and I encourage you to watch their talks because right now what I'm going to be talking about is the next step for the project, and that is to answer the question of where will Cosmic Explorer live. So again, using this notion of two-eyed seeing. On the left, this is representative of the exciting science that we can do with Cosmic Explorer. And on the right is a map of the ancestral lands of indigenous peoples in the United States. So just looking at this map, any location is the home to somebody or perhaps multiple peoples. And so we need to be very thoughtful about the way that we move forward when we're identifying locations for the Cosmic Explorer observatories. So as per the recommendations from the Astro 2020 decadal, the management structure of Cosmic Explorer really does embody the importance of the observational science, of instruments and observatories, of EDI, but also with partnerships with local and indigenous communities. So in the Office of Community and Land Partnerships, as per the call, there are folks with backgrounds and expertise that go far beyond the science. We have folks with experience in community-based initiatives, with education, with Indigenous law and policy. And this is a growing group of folks who are working on the process of building a community-based model for Cosmic Explorer. And one of our first charges was writing a land acknowledgement. So if you at your institution or your project are in the process of writing a land acknowledgement or have done this, you know how daunting it can be. So this is an incredibly important statement, and I encourage you, if you're in the process of doing this, to ensure that you set aside quite a bit of time to think deeply about what it is that you want to say, to research acknowledgements for, that may be for projects that are similar to your own or institutions similar to your own, to find something that resonates and feels like it's representative of what it is that you want to say. So ours, just to read it out loud, is that the Cosmic Explorer team recognizes the inherent connections between the lands, water, sky, and people. We're committed to cultivating connections to place. I'll come back to that in just a second. And partnerships with Indigenous communities who have cared for these places in the past, present, and future. And we acknowledge that we are responsible for the manner in which we do science and for the impact it has on the land and its peoples. So the reason I want to come back to place is that Indigenous people are fundamentally, deeply connected to place. And so understanding place is something that is necessary in order to build positive relationships with more complete communication between all parties. And I want to make a point to this end, and that is around environmental impact. So I'm going to tell a short story here around this notion. So last week, I went to visit LHO, and in the process of visiting the LIGO Hanford Observatory, I traveled to cultural centers for Indigenous communities that have an ancestral interest in that location, in the Hanford site. On the left, what I'm showing you is something called a seasonal round. So seasonal rounds are something that the Indigenous communities, they are all shared. And what it is a representation moving around like a clock of the seasons and the important parts of the environment as those seasons move on. So Indigenous peoples, in this case, have lived in these locations for millennia and developed an expertise about those locations that's deeply connected to the seasons and to the cadence of the wildlife in those locations. So moving around in the center, you'll notice that there are fish that begin very small. And the left-hand side, they're actually the eggs of salmon, and they go around and become red, right, moving around in these seasons. So what this represents is the salmon. And salmon are they're a deeply important part of the culture of indigenous communities near the Hanford site. And that's because the salmon runs going up the Columbia River, and all the rivers that feed into the Columbia River are really a central part of the traditional lifestyle. And so many of their lessons are based on salmon. And on the right-hand side, this is an image in the 40s. Color has been added. So this is an image from the 40s of fishermen using their traditional methods to fish for salmon in the Columbia River. Now, just after this photograph was taken, I think about a year or two, dams began to be constructed along the Columbia and rivers feeding into the Columbia, so in the Columbia Basin. And on the lower right-hand corner, this is an image of the opening of the Grand Coulee Dam with tribal leaders and standing in the foreground. So on the left is a map of the dams that were built over the next couple or few decades, all the way through the 80s. So over, I guess, about 40 years. So these dams then, you might already see where this story is going. Those dams blocked the salmon runs. And then ultimately, many of the salmon species were on the brink of extinction. And so only recently have folks entered into a conversation around this issue and are working in collaboration with indigenous communities to build salmon ladders, and the salmon populations are beginning to replenish. Now, I've told this story, but I want to add a layer to this, and that is that these dams are effectively some of the first sources of green energy. And so the excitement in building these dams and what they could mean for Washington state and surrounding states was something that was, this was something that everybody who was involved had stars in their eyes, because this was a way to move away from our reliance on petroleum products and to have and to serve the energy needs of those states. But because they had been built without being in consultation with local and indigenous communities, then they didn't have the background understanding of the environment. So this was a completely preventable situation. And I think this is something that we see over and over again with construction of large facilities. And physics and astronomy, of course, we're not immune to this. But what we can do is begin the process in consultation with community members and learn from the expertise of their environmental expertise. So I'm going to go back to this slide defining community-based models, and then really think a little bit more deeply about how we can use this for facility design, management, and decommissioning. So in Cosmic Explorer, going back to our concrete example, so in Cosmic Explorer, we are in the stage of trying to identify locations that can house a Cosmic Explorer facility. And so part of the process then is going to necessarily include consultation with local and indigenous communities that allows for those communities to be part of the decision-making process and builds in flexibility to respect, going back again to the timelines that for decision-making processes, particularly for those indigenous communities. So then what does that look like? As part of our proposal that was recently recommended, we had to write this into the NSF proposal. So which was one of the most difficult proposals I have ever written. And that is because flexible timelines is not something that naturally yields itself to an NSF proposal, right? So the way that we did this was we are beginning with an education of that is of the larger landscape, so that we're evaluating using public data, the physical landscape, so that we can better understand locations that will physically house a cosmic explorer observatory. And you can imagine that those are generally places, that are very flat, given the length of the beam arms. But in addition to that, we're asking questions about the sociocultural landscape, so that if we find locations that appear to be optimal on both of those axes, then we can enter into consultation in an educated way. And so what I'm showing here is several sort of idealized workflows or timelines where we may find that one location seems physically optimal, but is immediately not optimal in terms of the sociocultural landscape. There may be some back and forth. There may be something that immediately everybody's excited and the landscape is perfect. And because we're doing these evaluations in parallel, then that allows for flexibility at any one site, so that we're able to identify a handful of locations by the end of this 3-year period. So finally, what I want to say is that gravitational wave science is a global endeavor. It's something where it's necessarily strengthened by having observatories and a body of scientists around the world. But when we look at the landscape, this is similar to the landscape that I showed earlier of the United States. When we look at the landscape in terms of ancestral lands for indigenous peoples, then almost every continent around the world has large indigenous populations that have an interest in those locations. And so this allows us the opportunity to build from what we've learned and to enter into community-based models for the physics that we do. And so this website here, nativeland.ca, this is an excellent website. You can go to your location. I use this when I travel just to gain a deeper understanding of the places that I am. So I think I will skip this. Oops. And just say that two-eyed seeing, or something similar to it. In other words, being able to hold both the scientific excitement and connections and relationship building with indigenous communities allows us a depth of perception and to be able to open a third way. Gravitational wave science is a collective endeavor, a worldwide collective endeavor, and we've developed the problem-solving skills to probe the farthest reaches of the universe and some of the most extreme physics. So using this approach is certainly challenging, but we are up to the challenge, right? We know how to engage with challenging problems, and this is no less worth our effort and attention. So I hope that I've convinced you that, in fact, it's necessary to adopt a community-based approach to facility design and management at every stage of the process. We can frame this in terms of risk management or ethics, but in fact, I think that the best representation or way to describe this is just raising the bar in the way that we engage, and the way that we do science, and the way that we conceptualize what it means to run a facility. And with that, I think I am at my end. So Yakuke, Ora, thank you. My contact information is right here. Please feel free to reach out with any questions. I would love to chat with you about it.
Thank you very much, Kathryne, for the very stimulating talk. I think we can, we have, of course, time for questions. So either you ask to speak or put the question in the question answer window. Scott, go ahead.
Yeah, thanks a lot, Kathryne. That was very thought-provoking. I agree, and I really appreciate your comments. So I had a question on the practical side, which you alluded to, about the proposal to the NSF. Flexible timelines in order to do this, very thoughtful approach and deal with two-eyed seeing. You mentioned that the funding agencies have trouble with that, and I was wondering, do you think there's, what is the outlook for the future, or what are ways that we can improve the way that we deal with funding agencies to make them or help them be more flexible in timelines so that we can try to do these processes? Do you have any thoughts on that?
I do. I mean, I think that the first thing to note is that funding agencies themselves are undergoing a shift. So, for example, the General Counsel of the NSF has been deeply thoughtful about Mauna Kea. At this stage, the question at the NSF is, at what point do these notions sort of like trickle down to each of the divisions? So the astronomy division is much more receptive at this stage than other divisions, but that is something that is rapidly changing, including with the recommendation of these proposals. So that's one thing. The DOE, for example, is now, there's a memorandum from the Biden administration directly aimed at the DOE, and the DOE, where that directorate is for them to engage with in working groups that are composed of folks from the DOE and also folks from indigenous communities. So that's the nation-to-nation consultation component. So that said, for us, meaning those who are applying for funding, I think that's, the first step is to recognize that that is a changing landscape, and that the people who are reviewing these proposals are also becoming increasingly aware of the notion of community-based work. So I firmly believe that by simply putting something in there, that we are each as individuals doing the work of recognizing those changes are necessary. And as far as, what we did, we had to be very thoughtful, and we had a week of the leadership from Cosmic Explorer. We went on a retreat and we spent a week really thinking about all of the proposals, but one of the the proposal around how to do community-based astronomy was one of the larger conversations that we had. And so every project is going to be different, so it's hard to give a sort of blanket statement around that. But for us, what that process looked like was many iterations and creative thought, and it required that we have folks from outside the physics community in order to really conceptualize what that could look like by modeling our proposal after proposals that have and work that's been done in other disciplines. So I don't know if that helps, but I hope that it at least opens some windows, and I'd be happy to talk to you about anything that you're working on more specifically around what sort of model might work for you.
Great, thank you very much.
There is a question by Chad Hinshaw. Oh, you can open the mic.
Yes, hi. Thank you for the very nice talk. Very interesting. I was just clicking around a little bit on the Native Land website, and I noticed that many of the territories overlap. And I was just wondering if you could comment on some of the difficulties of negotiating with multiple indigenous peoples, or if that's a consideration, for example, Cosmic Explorer's location in the future.
Yeah, I mean, so I don't know that it's necessarily a difficulty. I think with that, so there are many reasons that territories would overlap. One of those reasons is that on that particular map, and it's worth just mentioning that it isn't complete. It's a work in progress. Is that, many indigenous territories were not territories in the sense of the way we think about territories in the Western sense, where there were strict boundaries between the two. There were shared lands. So Hanford was actually an excellent example of that, where at the Hanford site specifically, and other locations along the Columbia River, those were actually meeting places for multiple tribes to come together in the summer season or something along those lines, to share cultural for cultural engagement and other trade, etc. So what that can mean is that there are tribes that have a connection to that area have a very long history of collaboration, and the communication and the structures between those tribes are actually well defined. In other cases, it can mean that there have been tribes that have been physically removed from one location and placed on the territory of another. So Oklahoma is an excellent example of that. So there are many tribes from the eastern seaboard that have been moved to to Oklahoma. And so those grounds may be, you might have a location that's both Chickasha and Comanche, because that is the Comanche ancestral lands, but the Chickasha reservation is on those lands. So it can mean any number of things. Those are just two examples. But as far as the challenges for laying out a concept for what community-based astronomy or physics might look like for a facility like Cosmic Explorer, then the most difficult part, I would say, at this stage, is ensuring that we do identify all the parties that have an interest. And so I want to emphasize also, this isn't just indigenous communities. These are also the communities that live in those locations. So, landowners or your local hunting club or whatnot, right? So we need to ensure that we're in communication with all parties, because otherwise the tensions can grow in ways that make the project intractable moving forward. So I think that is one of the larger challenges, is and Mauna Kea, actually, TMT on Mauna Kea is a great example of how important that component actually is. So thank you for that question.
Question? Well, I have one, if I may. In one of your last slides, in fact, you've shown many in different continents the overlap of territories, but in fact, I don't know whether some data are available in Europe and Asia, and perhaps there the situation is a little bit different. But I think that there is a lesson also for this continent. Did you have the opportunity to compare this situation with the situation that one might meet in, say, Europe or say Asia?
Yeah, sure. So actually, can you see the map? I tried to put it up, but I'm not sure if it's sharing my screen anymore. So the answer is yes, certainly. So you might be surprised if you look in Europe, there are indigenous communities, and also in Asia. So these are things to keep in mind. And oftentimes these are communities that have been marginalized historically. And I think engaging is, can only be positive moving forward. So that said, even in North America, what that looks like is very different between what you might think would be similar. So, for example, United States, the history of indigenous engagement in the United States is very different from Canada, is very different from Mexico. So every every location has a unique history, and the landscape of what that looks like currently and has looked like historically is specific to those locations. So beyond saying it's worth paying attention to and it's worth thinking about, I can't give any specific, recommendations, but I think, but there are many resources out there, even in an international sort of global perspective. There are tools and resources to help navigate what that looks like. So yeah, and if you do dive into that in Europe, it sounds like, for example, I'd love to hear what you learn. Yeah.
Thank you. I think the advice is good also on this side of the pond, I guess. So I don't see any further question. You left your contacts too. Yeah. So I think that we can thank our speaker again. That's for clapping for everyone. And so thank you again, and we will meet then again at the hour for the last talk of this plenary session. Thank you to all.
Thank you.
We are at the hour. So let me call Kaze Wong for the last talk of this plenary session. And so how can AI help gravitational waves? So I'll warn you 3 minutes before the end. Thank you.
Okay. Let me just set up my clock so I'm also aware of where I am on. Okay, awesome. Thanks for the opportunity, for instance, the organizer for giving me a great opportunity to give this talk. When they first reached out to me, the title was actually not how can AI help gravitational wave. The title is like, okay, so do you want to talk about can AI revolutionize gravitational wave? And I thought to myself, wow, that's an aggressive title. So I instead of answering that question, I put it in like a more mild way. It's like, how can AI help gravitational wave? So and hopefully I give you some sense of what can it do? Will it absolutely demolish everything before? Because revolution to me is like, change a lot of things and, demolish a lot of that. So not quite, but it can certainly help. So the question is really, how can it help? To what degree artificial intelligence or machine learning, this emerging new method, can help gravitational wave? By the way, because of like this title is like heavily machine learning based, if you have a phone that you can have a QR code scanner, then you can take out your phone, scan the QR code on the left, lower left corner, that will give you access. It'll bring you to the website to basically the whole slide. I would advocate if you do that, don't advance the slide too early because there's like a surprise at the end. So let's not break the magic. But okay, let's go. I'm Kaze Wong. I'm a postdoc from Flatiron Institute. And today I'm going to talk about that. So recently, must be like, if you're any remotely on the internet, like looking at news, there's a lot of hype from the artificial intelligence community, machine learning community, deep learning in the last couple of years. And this is a painting that is generated by a machine, that people submitted to paint context without, the organizer didn't know this is a piece that is made by AI, and they actually nominate this to be the winning piece. And then whoever submits this piece to that contest, reveal that, oh, this is actually generated and made like a whole hoopla of like what generative AI can do. And this is one example of like, this AI hype, how it changed the society. And even Times, put ChatGPT, which is one of the things that you probably heard of, but basically it's a very smart AI-powered chatbot on their cover. So it's certainly making some noise in the broader society. And if you look at the search, the interest over time, this is from Google. You look at the search of the interest over time for gravitational wave, you can see it's peaked at 2015, which is where the detection comes in. And since then, it's been rising a little bit, like comparing to before detection, but it's, relatively moderate. Whereas if you look at artificial intelligence in recent year, really in the past 2 years, it exploded, and we're still going. Like, we haven't seen the peak of interest in AI yet. And then I put them together on Google and just say, it's not a varimetric because there's a big normalization factor somewhere, but you can see how the hype generated in AI has dwarfed gravitational. Of course, if you think about it, the broader society, very few people know about gravitational wave. It's mainly our community, but like, anyone is on the internet, on Earth, having access to internet, it's more or less searching for artificial intelligence related stuff. So the interest over time on artificial intelligence and machine learning is really big these days. Now that may make you feels like this talk is all about hyping you up, but I'm actually taking it into another direction. I work on machine learning and gravitational wave a lot, but a lot of this hype generated on the broader internet is really just that. It's just hype. And like, a lot of this interest generated for the broader society does not necessarily mean that we should be as hyped about using artificial intelligence and machine learning on gravitational wave. And today I'm going to tell you what can it actually do. And I won't just show you the good thing, but I'll also show you some failure that, what AI suck at, right? Like, because scientific questions are very specific subsets of questions that we solve in a broader society. And AI is not a magic pill. It's not a silver bullet that's going to solve every problem exists. And in fact, AI is very narrow in solving a specific kind of task. And hopefully today I'll give you a sense, a taste of what AI can do for gravitational wave. And I'm going to illustrate this with only inference, which is the thing that I'm most familiar with. And obviously I can't cover everything, but this extended to, other problem in gravitational wave and be like in the broader astrophysics community. This extended to searches, simulation, and something else. Okay. What is one example of artificial intelligence or machine? I'm just gonna, use machine learning, artificial intelligence, deep learning, all interchangeably, so I don't confuse everyone. Okay. So the first example that I want to bring to your attention is simulation-based inference. So what does simulation-based inference mean? So one of the tasks that we have to do quite a lot in gravitational waves is, I give you the data, you need to tell me what in the universe generated this data? What is the parameters for the source that generate this gravitational wave, for say? And this is not a unique problem for gravitational wave. There are other communities that do this stuff. For example, the cosmology community. In cosmology, we observe a lot of galaxy cluster, large scale structure in the universe. And there's a lot of structure in these things. And what people do is they generate simulation through n-body simulation, mesh code, to generate simulation of the universe. And then they train a machine to compare their simulation to the data that they have. Okay, so that's a task that you can do. And also in the particle physics world, like, you have a collider, but simulate, like, to really go through every calculation or simulate the entire collider, it's very expensive. So what you do is, like, you generate some small sets of simulation, and then you piece them together with machine learning. And after that, whenever you have data that actually you took from the actual instrument, then you can compare with that machine learned version of your collider or your detector with the data. Then you can have some understanding of what you have detected in the data without going through very expensive computation. So the name of the game of simulation-based inference is really like a title in this slide. You simulate something, then you train a machine learning algorithm to learn how the simulation looks like as you vary some knobs in your simulation. Then you compare with the data. Okay, it usually involves some very expensive simulation. Then you want to use machine learning to speed them up and compare to the data. Okay, so that's simulation-based inference. Simulate, train the network, and compare to the data. All right, and in gravitational wave context, this has been, very nicely done by a group. But the scenarios is basically the same. You're given some data, okay? And we can simulate data to a very high fidelity, right? We have very good understanding of detector. We have very good understanding of model. And the only problem is if you have ever do parameter estimation in gravitational wave, at least in the past, it used to be a very computationally expensive process. It takes somewhere from a day to a couple of weeks to infer some properties of a particular event. And that is a price that we don't want to pay as we go, forward and have more and more events. So the name of the game is I can simulate how my detector work given some astrophysical source. Can I infer the source properties very quick in gravitational wave? Strain in one side, posterior out on the other side. And this has been very nicely done by a group from Germany, led by a student, Max Stax and Stephen Green and some others, that they, with Dingo, their code, I don't know whether you can see it clearly, but MCMC used to take a day. But for this, I think this is one illustration of an event that I don't know whether it's injected or like a random real event. But the point is, you can get to a very high fidelity posterior in just about 20 minutes. And they have some complicated algorithm behind that use something called normalizing flow. But the technical detail is not too important here. But the idea is you train the network to have some understanding of the PSD and the strain data. There's some extra trick that they do to shift the time to make it more robust and all that. But there's some network that you learn to represent the PSD and your strain data and your model. And then you can sample it very quickly. And as they illustrate in their tweet, it takes about 20 minutes to infer I think it's a real data. And on the lower right here is showing one of the results taken from their paper. The corner plot is just to show you it's highly, it's very similar to what the posterior given by Lau inference MCMC in a full, I think it's a 15-dimensional inference. I think this is the first event, GW150914. So there is effort put into making parameter estimation much faster using neural network, and it works quite fine. This is actually a series of study that I personally like a lot. Now, this is a single event. So given the strain, tell me the source parameters. And these days we have bigger and bigger catalog of gravitational wave events. So not just one event, but a series of events, a set of events. Okay, so can we do this also on a population level? And the answer is yes, you can do that. So this is from a study that I do a couple of years ago. So instead of taking simulation of the detector and GR model, our waveform model, what you can do is do a population synthesis simulation. So in this study, this is a figure taken from one of my paper. Oh, by the way, all the links, citations are all open. My slides is completely open. It was in the QR code. If you go on my GitHub, you can find, the source code for the entire slide. So if you want any reference and all that, it's all there. So don't, worry about not being able to fetch any citation or reference in our slides. Okay. So the idea is if I have a population synthesis simulation, let's say cosmic or CMC, this is either isolated simulation. So these are binary that evolve all along, or in a cluster environment. If you can simulate that, so these different lines are different simulation in that particular simulation suites, okay? So this is just showing the probability distribution of the primary mass in one particular simulation, or three particular simulation from cosmic, and three another particular simulation from CMC. So we basically simulate a grid of this simulation, and we train a neural network on them. And then we can ask the question, we can invert the problem. We can ask the question, what is the mixing fraction? What is these parameters are? This is the common envelope parameters, if for people that who knows. Some parameters that govern how massive star binaries evolves. And RV is the size of the cluster, and F is the mixing fraction. So once you train on a grid of simulation, then you can invert the problem. You can say, okay, then given the observed catalog that we've seen, what is the most probable parameters that is, favored by the data? So if you trust our study, then the conclusion that we got out of that particular study is most black hole binaries are from cluster. Now the question is, should you trust us? And like, I mean, this is the same story as the single event inference. Should you not trust us? But, you know, I don't really trust this study, even though I did it. And there's a reason for that. Now let's take a moment. Oh, wrong slide. Let's take a moment and think about it. Hopefully you think that like the first one is a little bit more robust, or the second one is like less robust, or at least I can tell you that, you know, that's how I think. And let's take a moment and think about it. Why is the first example more believable if you think it's more believable? All right, like if you think the second example is more believable, then we can talk in detail. But hopefully I show you that, you know, the first example is more believable. And why is that? So let's think about the characteristic of the two problems. And what is the lesson that I've learned from these two simulation-based inference scenario? So again, simulation-based inference is quite a simple idea. If you can simulate some signal or some data, right, then you train a neural network to approximate that, then you can compare with data. And we just did that for both single event inference and population inference. It should be the same thing. What's the difference between them? What is like, but before we go into that, I'm going to show you the punchline later. But let's think about what is the perk of simulation-based inference, all right? So one of the perk is obviously very fast inference, as we've seen in the single event inference case, that it reduced this inference time from days or weeks to minutes, okay? So that's great. You don't need to, you know, spend a lot of computation. The second thing is, it's usually very easy to retrain your network. It's the same infrastructure. If you have new simulation, you just press the same button and you train the network and it goes, right? You don't need to retune everything and change all the formulas about your likelihood. So that's pretty easy on the human side. And it's very flexible assumption. As long as you can simulate it, you don't need to write down a specific closed form for your likelihood. As long as you can simulate it, you can do inference. And it's very simple and very easy on the human side. However, there's some danger that comes with it. So one danger is, I call it, why is my math negative problem? So it's basically, once you train something on a simulation that you, in principle, fully understand, then you lost some of the fidelity in the simulation, because training is never perfect. And if you do, let's say you do a single event inference and you didn't train your network very well, you didn't regularize it very well, and you have some posterior that goes into the negative mass region. You have two things that you can do if you see that. Like first, it's like, there must be a bug, or you can declare that your training is imperfect, or you go to like try to apply for a Nobel Prize. You say, oh, we found negative mass, which is obviously dumb. You shouldn't do that, right? So there's some dangers that's associated with simulation-based inference that, you know, once you train on some simulation, you kind of lose some fidelity. There's very hard to guarantee that you're always doing the right thing, okay? And the other thing is, it's actually a lesson from the second scenario, the population inference. So if you recap, a little bit short recap is like simulation-based inference. The first step is to simulate, right? So we first simulate a bank of simulation. So that already takes compute, right? It takes some computation for generating the simulation set. And then you train, there's also computation. And then you do an inference, right? But if you can train, like if you already have the bank of simulation, why don't you just compare them? Do you actually gain anything? There's something that you gain, but is that really worth it? You do gain some efficiency when you do the inference, but if you have the simulation set, you might as well just compare them. It's probably just gives you the same conclusion. So are you really winning? Are we really winning when you use SPI? That's something to think about. And, you know, lastly, and when I say, you know, it's very easy to retrain them, it's very low in human cost, but computationally, they still cost something. And do we want to keep paying the computational price again and again? That's something to think about again. So now let's review the ultimate lesson from the two SPI scenario. What's the difference between the two? So if you think about the first scenario, when you have single event inference, you have one very well-defined model. It's the same detector. It's the same waveform model, hopefully. And you have changing data. And then you can apply a simulation-based inference pipeline machine again and again. And then, you know, you really win. as long as you make sure that it's like regularized finally, you don't need to worry about the first, you don't need to worry about too much about the first danger of SPI. And you can be sure that you're winning because you're applying the same pipeline and again, instead of like consistently retraining. So the second and the third point of danger is mitigated when you have a fixed model and changing data. Whereas the second SPI scenario, our catalog is a fixed size. You know, now it's growing, but after we finish taking data, it's the same catalog. The data is somewhat fixed, right? Whereas in population synthesis, people really want to change their model because it's not a very standardized model. So we're continuously retraining. In the end, we don't really win. So hopefully this is the first message that like it should be somewhat evident to you now. When we apply machine learning or AI, if you have a fixed model, especially simulation-based inference, if you have a fixed model and you have changing data, go for it. It's what AI is good for. But if you're consistently changing your model, then you may want to rethink whether you really want to use AI or machine learning. So that's the first point when we have this black box kind of machine learning algorithm. This is the lesson that I kind of learned. Now, the next thing is like hybrid method. I'm a big fan of hybrid method. And what I mean by hybrid method is like you have some traditional method, for example, MCMC, which I'm going to get to very soon. And instead of replacing the entire MCMC machine with machine learning, which is simulation-based inference, right? We bypass the entire sampling step. We just replace the whole pipeline with simulation-based inference pipeline. So that was what we did. But I'm actually more of a fan of hybrid method. Instead of abolishing everything, we take part of our original pipeline, let's say MCMC, and swap that with machine learning. Now I'm going to illustrate a little bit more closely. What do I mean by that? Now, AI is cool. There's a lot of hype. There's like this end-to-end training, but the infrastructure around AI is just as cool. And it's a better example to illustrate that with JAX. So JAX is a library or a package, Python package that is developed and maintained by Google that support a number of features. So these are not directly AI thing that people usually talk about, but these are features that people come up with infrastructure to support AI research or machine learning research. So JAX allows you to do a couple of things. If you write a function in JAX, it's just like NumPy. You just basically write NumPy code, as you can see here. Let's say I write a tangent hyperbolic. And now I want the derivative with respect to the parameters x. Instead of working that out by hand or taking finite difference, what you can do is to use something called automatic differentiation. So it's basically a code transformation routine that you look at the source code and the primitive and just replace them by some other operators or other primitives. Think about sine x. If I want to take the derivative of sine x, then it's very easy. Everyone knows it's a cosine x. But any computer program is basically a tree of all these operators. So what it can do is go into the source code, let's say your tangent hyperbolic function, and just replace that with the derivative operators as given in JAX. So it has a couple perks, it's faster than, usually more scalable than finite differencing. It's basically machine precision accurate and stuff like that. Okay, so this is one infrastructure that it's very critical for AI study because AI has millions of parameters. Without autodiff, they cannot tune any of these like machine learning or neural network. So that's something that we can use. We don't necessarily need to do AI, but we can take advantage of autodiff. And there's a couple more perks like simple vectorization, just-in-time compilation, simple GPU integration and stuff like that. These are all infrastructure available in in JAX. This is one example. It's available in JAX to support AI study, but we can make use of this without going to the AI part. Okay, so there's autodiff, there's compilation and GPU and all that. Great. So the infrastructure is really cool. Now, what we can do with the infrastructure is, so one thing that a friend of mine did, like Tom Atwood, is to make gravitational wave waveform in JAX. Okay, so Ripple is a package that you can find it on GitHub. You can download, pip and install and all that. There's a couple more packages like GWFast and other package that does similar thing, but like this is one package that we engineered on our side. So this is, do I have, yeah, okay. So this is a package for gravitational wave waveform injects, and like long story short, like typical like one likelihood call, if you use a traditional library like Lao, it will take about a millisecond to evaluate one likelihood, or so on. So this is ballpark estimate, but like this is how usually the number goes. Let's say a millisecond, okay, for IMF and MD. But once we put these waveform model injects, now we can do automatic differentiation, but also we have access to GPU acceleration just natively, and we can do 10 to the 6 likelihood evaluation in a second, or about 1,000 of them in a millisecond. So no, wait, 100 of them in a millisecond, I think. Yes. No, 10 to 3. Yes, 1,000 of them in a millisecond. So just by putting a gravitational wave waveform, writing that into some AI infrastructure, and suddenly we gain computational efficient. Of course, they have engineered the infrastructure to be very computational efficient, and we're just making use of that. So this is one example of like hybrid method. Instead of just replacing everything, we really just take our model and put it on some more modern computing environment that it was designed for AI, and that already gives us the computational edge. The next thing that I did is like, this is more a package that I made. It's called FlowMC. So instead of like, this is just like a list of feature that we have implemented in FlowMC. I want to like speed up a little bit, so I won't go into each of these functions. But basically, it's a package that instead of doing a traditional MCMC, it used some machine learning component to learn the proposal on the fly. And like, here's an animation to show you like briefly what it does. So in the normal MCMC, let's say you have a target that looks like 2 moon. And what we do is basically, in a very broad sense, we're drawing Gaussian and throwing costs, like tossing coins with the normal like the simple Gaussian, and trying to do a random walk in this 2 moon distribution. And you can see, because the proposal is very local, you don't really get the chance to jump and explore the other side of the target. And what you can do is like, as you generate data, so you have multiple of this chain, instead of using one chain, you can have multiple of them. And as they generate data, you learn the proposal on the fly. So as we generate more and more data, you learn the proposal on the fly. And later on, you use that proposal in your MCMC. Now, this is our target again, is shown in blue. And now the green is the learned proposal. It's not perfect, but then you can start jump around the 2 target. And that helped expedite our MCMC a lot. So we put Ripple and FlowMC together in a package that we call GIM. And now, without abolishing everything that we know about gravitational waveform model or detectors and something like that, we'll also be able to do basically minutes scale gravitational wave inference. So on the left, it's a parameter estimation run with GW150914. And it's basically the same as the benchmark, which is Bilby in this case. And we actually take this further and we simulate a population with around 1,500 events and do inference. And this is the PP plot. So when it is diagonal, it's basically showing your method is not biased. So we can do also fast PE very robustly without abolishing whatever infrastructure that we already have. So this is an example of hybrid method. And I'm a big fan of hybrid method. I really don't have like bad thing to say about it. I'm cleaning the code up. It's more available and easy to read in. Stay tuned in the later month in August. And I'm gonna skip the next slide. Okay, so hybrid method, instead of throwing away everything we have and just replacing things with machine learning, we can also just infuse machine learning into our traditional pipeline. So that's one way to use it. And now I'm going to get to my third point, is like, instead of using machine learning to actually do the task, we can actually use machine learning as an inspiration. It's like, for example, and I'm going to illustrate this with model design. So one challenge in population analysis is people need to write down a model to analyze the catalog. For example, whether it is like a truncated power law, broken power law plus peak. someone need to write down the form before they can analyze the catalog, because gravitational wave event is very noisy. As we have more and more data and we have more and more resolving power in the parameter space, it's a little bit more difficult to build all this model. And also because it's written by people, it's very hard to go to high dimension because you need to write down a very complicated form. And the main problem that I see this is like, these forms are powered by smart people, and there's a limited supply of smart people that we have in the world. So if they're busy, we can't just like, okay, give me a form, right? So it's not very scalable, both in, the complexity and the human power aspect of it. And in the latest iteration of this, people start to throw more flexible model like a spline onto the model, and it suddenly become less interpretable. So this is a challenge. How do we write down models for population analysis? So instead of really writing down the form, why don't we just use some very flexible population model? So in one of the study that I made is like, we again use something called normalizing flow. It's very flexible machine learning model to try to model the gravitational wave population. So on the left, you see all the different posterior in the primary mass for all the events. And on the right, it's what's this flexible model. It just has a lot of parameters to trying to understand and fit how the population, like the primary mass function should look like. I need to say that, we are not the only people that does that. There's like other people like Stefano and Didi. I think that's his name. That does like some Gaussian mixture. And there's some other people that do flexible modeling of the population. And you can do that. It's basically throwing, let's say, a mixture, like giant mixture Gaussian, a very flexible machine learning model to it, to try to just model what the data is saying. Now, okay, we can do that. We get a description of the data, but have no clue what the machine learning weights means physically, right? I cannot unfold the normalizing flow and point to one of the parameters, say, that's what it means. That's not what I can do. So instead of stopping here and just modeling the data in an uninterpretable way, what we did with Miles, a friend of mine, is we use some techniques called symbolic regression. So if you give me a line, instead of Taylor expanding it or fitting it with a polynomial, what you can do is like you use some genetic algorithm to come up with what is a good functional form to fit the data. And symbolic regression has a couple of advantage comparing to just polynomial or other fit. It can do really flexible stuff. It can come up with quite a complicated form that is usually not favored by a certain class of methods. Imagine if you have a 1/1 minus x, and you want to represent that with a polynomial. You need quite high order of polynomial to represent that with some acceptable accuracy. Whereas symbolic regression can just get you the equation, and without going into expansion. So that's some techniques that we have. I mean, Miles developed. It's in a package called PySer, publicly available on GitHub. Go check it out. It's pretty cool. And so what we did is we took our very flexible model, fit it to the data, get some understanding of it, but that we cannot interpret it. But then we take this result, now we get a line. We're trying to distill some physical understanding of that from using symbolic regression. So in the end, we get actually a functional form. And in fact, this is a study that I did with Miles. Again, link is in the GitHub. Don't worry about the link. We actually say that, actually a power law plus a peak is a good description for the data. And in this process, we don't need to write down any form. We just like say, okay, this is the data. Now machine learning, go. Once you fit the data, we just use symbolic regression to kind of tell us what is the form. Now, the good thing about this method is once it tells you the form, you have all the rights to just take the form and verify it however you would. Just like you tell a grad student, okay, come up with a form. Now, instead of asking your grad student to come up with a form, you just ask the computer to come up with the functional form. And then you can do all the analysis to check that form, whether it's like you can check space factor, you can refit it with like hierarchical Bayesian. It's just as valid as having a grad student telling you the form. So yeah, like this is what machine learning should be used in general, I think. Instead of trusting the form, trusting the result, what AI tells you, you use it as a proposal. You just say, okay, you give me this form now I'm going to test this again. And in that way, we can actually make robust discovery, right? Okay, so I'll give you a couple examples of what machine learning can do for gravitational wave. Now, what is my vision? Like, this is very personal opinion, so don't take it with a grain of salt, but this is my vision for the future. There are more open questions than just inference in gravitational wave. There's searches. There's huge effort into searches. I'm not an expert on this, so I didn't talk about any of that, but there's huge effort into searches. And there are simulation that goes in, like SXS, to simulate numerical relativity simulation. So there are also some open questions that can be addressed by machine learning, I think. And of course, there are more inference that people haven't sorted, like, for example, LISA inference or 3G inference that potentially can be benefited by machine learning. So these are open questions. I'm sure there are more open questions that can be, categorized in more fine-grained category. But what do we really need to do? Is that just throw whatever off-the-shelf machine learning algorithms to it? I think there's a couple of things that I see this will be great in the future. We have this. First, I think we should build more hybrid models, because again, hybrid model is really just taking whatever originally is there and change a tiny bit within. And if you don't do that, it's just the original model, so it's not going to suck more than what is already there. So hybrid model is just a way to make the existing infrastructure more performant and flexible. And the next thing is, like, if we don't want to go deep, then think of machine learning as a very flexible proposer. Very flexible model that just can learn very complex data, okay? Because it has a lot of parameters. So that's one way to think about how we can use AI. They're just very, very flexible model that we can understand the data that we given. And finally, the infrastructure that is built for AI allowed us to think very scalable compute. Instead of spending 5 years to think like the perfect kernel for a particular computation, maybe it's also worth thinking about, how do I use this infrastructure to make my computation more scalable instead of just, more efficient, right? Because like computer is getting cheaper and cheaper, and electricity is getting cheaper and cheaper. Well, electricity is not necessary, but computing is getting more cheaper over time. So being able to leverage scalable compute is something that we should think about when we attack any of these problems. So one thing I really want to sort of end with, I still have a couple more slides to go, but before I go to them, the main thing that I personally think AI is like their infrastructure. They're not meant to replace human. They're not meant to just, we get an answer and be done with it. Their infrastructure. There are things that we can build and coexist with the current pipeline and people in the way. It's not just a flashy way to publish paper and, get the answer. They're really infrastructure, and we should think in terms of all this infrastructure illustrated by simulation-based inference, hybrid model, and model design. Now, whatever I said before is general. It's tailored to a specific class of researcher that is care about inference and so on, or care about AI in general. But this is one last problem that I want to mention to everyone. Now, everyone should come back and look at the screen, because in the next 5 minutes, I'm going to tell you something very important, and it's going to apply for everyone. Trust me. So I made this poll a couple of days ago. It's like how people spend their time in scientific research. And most people said, I spend a lot of time reading literature, writing paper. This is like the unhinged session of my presentation, which I love the most. So some people spend reading. Most people spend either the time in reading literature, writing paper or grants, or writing code. Very few people spend time really figuring out the math and figuring out what's going on. That's sad, no? So I think if you don't care about any using AI in your own research, do this. We can do I think AI, the most impact that AI can do for science is to change our workflow. For example, now I'm gonna go into crazy territory. For example, I can go to an AI power engine to ask basically a ChatGPT with citation. There's something called Perplexity. I can do literature search. Tell me something about gravitational wave and machine learning. Okay, so this is if you don't know about this is a Perplexity, and it's basically ChatGPT with citation. Okay, And it actually gives you related question as well. It's like, what are some of the specific machine learning techniques used? I was like, I don't know, like, and I click on it and you can find more and more. And it even gives you papers. Okay, so these are real links that you can click on. And you can do literature search much faster in this way, because now it can digest paper for you much faster and understand the literature much faster. So you don't need to spend that much time. It's basically creating too long, don't read. And it's interactive. You can just ask question. And it's asking question. In the interest of time, I'm not going to go too deep. If you're interested, like hit me up. I'm going to show you all the tricks that we have to ask this question. So literature search, machine learning can do that for you. It can write paper and grant. It's pretty sick. I was trying to let's see if I can get this right. Let's find one of the paper that I wrote. This is a paper that I recently put out with my student, and let's do this. We can actually write paper or grant proposal with it. And I'll show you. This is pretty concerning if you're not watching. Let's see. Let's say I open a new chat. I paste this guys in, and I can ask, suggest some follow-up work given this paper. Okay, I know some people are aware of these, so like you may say, this is lame. But for people that don't know, this may change how you think that science can be done, because this is basically our workflow. So this is a paper that I wrote with my student. I just put it out recently. And I just asked it to suggest some of the follow-up work. What is the follow-up work that you can do? And these are the follow-up work. Some of them is reasonable. Oh, this is actually very reasonable. I'm open on PV3. It does not exist, but that's okay. But it can actually write papers. And again, in the interest of time, I'm not gonna like go too deep into that. And finally, this is my favorite demo. It's coding. So my day job involves a lot of coding. And one thing that I hate is to write documentation. And one thing that Copilot, this is a particular AI, it does my documentation for me. If you ever use my code and you see documentation, it's almost certain that I don't write them. For example, like there's a function, this is one of my code. There's a function that I didn't document. Then I can just like write a couple things and it should, okay. Sometimes it's, so it's trying to suggest how like I can just tap complete my code and it's suggesting all these parameters. I mean, actually just accept this. Yeah, it will suggest all the documentation for me. So speed up my work quite a lot. And finally, you know, this is something that like I'm actively building. It's called Agent. So if you have access to my slide, which is on GitHub, go look at this yourself. It's basically, instead of just writing, you can actually ask it to write shell command and execute it. And what does it mean? That like it not only can write papers, write code, it can execute code and reflect on code. And what does that mean? That it can run my code and do my project and give me a sensible summary. Anyway, I'm more than happy to talk about how, you know, AI can change your workflow. And I think this is de facto like the biggest impact that we're gonna have, like barring all the hybrid model thing. If you're not aware of like how AI can change our workflow, it's can do a lot, and I can show you how to do. But anyway, so this is my speed run of like how AI can help gravitational wave, and I'll take question. Thanks.
Thank you, Kaze. Thank you for the nice talk. Fascinating. And let's see for questions.
Oh, there's a hands up. Chat.
Okay.
Should I just
Fred, yes. Chat.
Thank you. Very, very interesting talk. This sort of thing makes me very excited, but it also kind of fills me with terror a little bit, because, you know, when we start doing all these things automatically, I feel like there's a possibility of losing some essence of science in terms of veracity, in terms of understanding exactly what is being done, and, you know, in terms of not just trusting these sort of black box results. I just wonder if you could comment on that and what you think about that problem.
Yeah, that's the reason why I'm a big fan of hybrid methods. So like, for example, I'll take, you know, like hybrid method is basically you still maintain some of the original infrastructure that you understand. And it's just really finding the one part that it's basically fitting the data. And where I think about waveform model. Waveform model is calibrated to some data, and people can write down the ansatz and do the fitting. But some part of the fitting, at some point, you just have too many parameters that people stop understanding that. Why don't just replace that part with a machine learning model? That's why I like hybrid model. I think we still fully maintain all the interpretability and just really leverage whatever fitting capability that machine learning has. So that's why I'm a big fan of hybrid model. And to illustrate on the other side of like, if we just blindly trust the AI, I'm very skeptical about AI, actually. That's why I like to keep human in the loop. When I use Copilot or use things to code, I exclusively don't use it to generate any code, but just generate documentation. And as you can see how I show in the last demo, I actually need to accept it. If it doesn't write, then I change it. So I think it's pretty important to keep the human in the loop and really to think robustly. And in the end of the day, when I think about science, it's really a question to myself. Do I understand a certain process in the universe? And whether there's something that out there that really doesn't matter to me, right? Like it's me have to understand it. So the AI cannot do that for you. The AI can read the literature and suggest literature to me, but it's on me to read the literature and understand that myself. So I don't think AI can replace that because ultimately it's on me, right? And I think I would highly advocate to try the tools, but those two I never advocate to just blindly press a button. It's usually integrated into some workflow. For example, if I want to write a grant proposal, instead of just generate a grant proposal, I can say, okay, suggest a couple papers that I can read, and I can go read them, or just find places that we can make use of the suggestion instead of just blindly trusting the AI. So that's how I see it. Does that answer your question? Okay.
Yeah, no, that's great. Thank you.
Cool. There is an anonymous attendee asking the questions of can it write annual grant report? So this slide is actually the source code. Let me share my screen a little bit. So I think this is what I ultimately want to get to, but for myself. So most of my slides is now in whatever it is HTML format. And with Copilot, it can actually start suggesting things. For example, if I say, type something here, as I think after I finish running, it'll suggest something, I can complete it. So the good thing about this language model is it's really flexible. And as long as you have some document somewhere, let's say you have your research well documented in a repo, then you can just really paste them. And this is sometimes I do that. If I have a paper I write a while ago and I forget what I wrote, and I just paste them in the language model and say, hey, okay, now summarize my own paper for me. Or for slides and presentation, I did that slides before. Now I write a little comment. Can you change this slide in that way? And it just does that. I mean, usually it does that to 80% accuracy. Then I say, okay, I need to change this a little bit, but it can kind of do that. If you have really well documented progress throughout the year, then I think it can get you a pretty good start in your grant report and say, okay, this is not the perfect one, but I just need to change it. So again, it doesn't completely replace your job, but it helps you to take just be much more efficient. You can totally try it. Like ChatGPT, paste a paper in and ask it to summarize it, or ask it to write a report. These things you need to know how to prompt it. But yeah. I wouldn't bet my life on it. I wouldn't just now generate a grant report. But it can certainly help quite a lot. Okay.
Thank you, Kaze. Other questions? Well, I have one. I have the impression that so the knowledge base is in text, in whatever you have, and also sometimes in one-time series. It was for the waveform, but with the detectors, we are getting mad with, say, 1,000, 2,000 channels that are time series.
Mm-hmm.
Do you have any view on how we would deal with this with the situation seems to me different? Maybe it's just the same, but it looks to me different.
I think so. So is the question that the data that I'm concerning now, it's one time series, but like if we want to leverage more information in the other channels, how do we do that? Is that the question?
Yes. Well, we have a detector that doesn't work, and we want to have it working. That's the
Yeah. I think the good thing about like this machine learning infrastructure is it's really flexible. So it doesn't matter whether it's one channel or 1,000 channel. I mean, of course, the compute will be different. Like you need to spend more time into computing more numbers, but ultimately they're just one time series or n time series. So they are really flexible into looking into let's say correlation into all these auxiliary channel and can pick things up. And human can't do that, right? Like people have a hard time looking at just like the spectrogram from the data channel and trying to glitch it. And imagine now we want to look at 1,000 channel spectrogram. It would be we need a lot of grad student for that. But instead of using grad student, why don't we use like more flexible and scalable compute for that? So I think they're fundamentally the same problem. It's just one time series versus an n time series. There's some catch, like maybe the sampling rate is not the same, so you need to do a couple of things to remedy that. But I don't see it should be handleable by whatever infrastructure. Because people do this like in finance, right? Finance is a lot of time series, so that's a good thing about machine learning. It's like they really just think in terms of like the data instead of whatever the model is. The model piece can be super complicated, but the database, data space is like, okay, time series, image, volumetric data, that's about it, or graph, that's about it. So there's not fundamental difference that I see between, 1,000 channel, which is just like stock market, versus one channel, which is what we're dealing with.
Thank you. I see that you have fascinated the audience in the chat, in the question and answers.
Awesome. Yeah, I mean, I basically live on GitHub. If anyone has issue, like more follow up of this, shoot me an email or find me on GitHub. Then I get back to them like almost like an unhealthy pace. So.
Okay, I think that we are at the end of our plenary session. I don't know whether Scott wants to. First of all, let's thank you again for the talk and for the questions. And whether Scott wants to say something to end up the session.
Yeah, just a quick thanks to Francesco for chairing the session, but also to all three of the speakers for three very interesting and very different talks. All three, I thought, very thought-provoking and very interesting. So thank you very much. And we'll get this up on the recording on YouTube within the next day or two. So thanks, everyone. And the next session is in about 6 hours, I think. So thank you.
Bye-bye.
Thank you very much. And we close the session here. Bye-bye.